Hi Year 11, good morning. So we're doing a lesson today on acceleration. So let's start with our KIP quiz today, and then later on in the lesson you will need a calculator, so make sure you've got that ready. So you can always pause the video now to get a calculator. But now you need your mini whiteboards, 1 to 5. I hope you guys actually do this, by the way. 1 to 5 on your mini whiteboards, and then match up these definitions with the key terms. So you can pause the video for a few minutes. Okay, so let's go through the answers. So number 1 then, the equation to calculate speed is speed equals distance divided by time. So we practiced that in yesterday's lesson. No, actually it was the day before, wasn't it? That was Monday's lesson. Number 2, the typical running speed. So this is 3 meters per second. Remember how I went on and on and on about how you need to remember the numbers. So typical walking was 1.5, running is 3, cycling is 6, and you have to remember those. Then this is the equation to work out acceleration. So we'll be practicing that today. And then number 4, the difference between the stretched and unstretched lengths of a spring. So that's the extension. And then 5, materials that are attracted by a magnet, they are said to be magnetic. So you can even take a picture of your board now just to prove that you're doing it. That would be nice to see today. So take a picture of your board. That could be one of the things you send in to us or upload on Google Classroom. Right then, so today, acceleration. So we need to be able to recall and apply the equation. So it's change in velocity divided by time. We need to estimate the magnitude of everyday acceleration. So the word magnitude means size. So we need to look at, for example, if you were to be sort of stood still and then suddenly you started walking, how fast would you be accelerating? We need to calculate acceleration from the gradient of a velocity time graph. So that's just like the distance time graphs, where you were taking the change in y, dividing it by the change in x. And then for higher tier, you need to work out the distance travelled under the area of the graph. So you'll be doing a little bit of a crossover with maths there, where we work out the area of a triangle or a rectangle using base times height or half times base times height for a triangle. You need to be able to draw velocity time graphs. So if you have graph paper at home, then you'll need some of that today. But if you don't, just use your exercise book. And then we need to apply an equation for uniform acceleration. So a slightly different equation there. Okay, so we call accelerating then speeding up, and that should be quite familiar in your head today. So when we speed up, we say it's accelerating. When we slow down, we are decelerating. So if we're in our car and you put the brakes on, then you're decelerating, okay? So on your mini whiteboard then, you've got these 5 options. Which of these 5 are examples of speeding up? So which of the 5? So you could just write the letters, but which of the 5 are examples of speeding up? So pause the video and then restart when you're ready. And then if you've come back after pausing, you should have, that is A, so a runner in the first second of a race. So you were stood still, then you started running, so you're accelerating. And then E also is a rocket being launched. You're having to put a tremendous amount of thrust to overcome the kind of sort of frictional forces and air resistance as the rocket is being launched. So that rocket then would be accelerating. So obviously B, a cyclist braking, that would be an example of decelerating. A C, a skydiver at terminal velocity. By the way, jumping out of a plane is the most awesome thing I've done. So it's really good fun. You should go do it. But a skydiver at terminal velocity, that means that they've reached their maximum velocity. And if they're at their maximum, it's not changing. So therefore, it's not accelerating, because to accelerate is to speed up. You're getting faster, but you can't get faster than your terminal velocity. So D then, a motorist driving around a roundabout at a constant speed. It's the word constant, that's the clue there. So they're not changing their speed, so it's not accelerating. So the answers were A and E for that one. Okay, so I think this would be the point to put this information on a revision card or to write down this key information. So I could see this in your books, please. So this is the equation for working out acceleration. So we say that acceleration is the change in velocity divided by time. And so we can use these letters here. So A, obviously acceleration, equals. Now that triangle, we call that delta, and it means change. So you could get like a delta temperature, and that would just mean change in temperature. But this is delta V, so it means change in velocity. And then you divide that by time, and that's how you work out acceleration. And it's important to note the units for this, that the units for acceleration are meters per second squared. So I would pause the video and I would write this down in your book. This is key information. We're going to use this equation in a minute to practice, or have it on a revision card, or both. That would be even better, wouldn't it? And if you're thinking, well, why do I need to keep worrying about revision cards? The exams are cancelled. Well, no, technically they're not. At some point you are going to do mock exams for us so that we can decide your final grades and then submit them to the exam board. So no, exams are not cancelled, just the ones that you were thinking you were sitting. Yes, they're cancelled, but you will still be doing some form of examination for us. Okay, so pause the video if you need to, but if not, I'm going to carry on. So here's an example then. So a car takes 8 seconds, that's a time, to accelerate from rest to 28 meters per second. Calculate the average acceleration. Now it's really important here that you know that anything that says rest means 0. If something is resting, it's stood still or it's staying still, it's got 0 velocity. So it goes from 0 to 28, which means its change is 28. So the change in velocity is 28. But what you do is you always take the final velocity first. So you take the 28 minus the 0, and it won't always be a 0, but 28 minus the 0 obviously equals 28, and that's your change in velocity. So we call the final velocity V, and that obviously is 28 in this example. And then we call the initial velocity U, and in this example, because it said it was at rest, that means 0 meters per second. And so therefore the change in velocity is 28 minus 0. So you always have to do what it is at the end minus what it was at the beginning, and that's 28 meters per second for this question. And then to work out acceleration, we would do 28 divided by 8, because that was the time. And then we work out our answer for acceleration is 3.5 meters per second squared. Okay, so you write out the equation, you put your numbers in, and you write your answer with the units. And it's just really important that you make a note that for acceleration, it's meters per second squared. So final velocity is V, initial velocity is U, and if a question says at rest, it means that the velocity is 0. Okay, so that's the example we can do together. Now it's time for you to have a go at these 5 questions. And obviously, if you get stuck at any point, we are available during the lesson, so you can just email us at any time. So you could email me, so ecraig@gloucesteracademy.co.uk, and I am online while you're doing these lessons, so you can email me and ask for help if you need it. So pause the video and come back when you're all sorted. Okay, so hopefully you've paused the video. If you haven't, pause it now, and then we'll carry on with the answers in just a moment. Okay, so let's go through them then. So the first one, and if you look at the right-hand side while I'm talking to you, you can see that I've got this layout, and I've been trying to model this to you whilst I've been doing different equations with you. So you're always writing out the equation that you need to use. So it's A equals change in velocity divided by time. So it's that triangle means delta, it means change. The V was for velocity, and then divided by time. And then put your numbers in. So from this question, the change in velocity was given to you as 14 divided by 2. You don't need a calculator for that one. And why have I written the answer as 2 when it should be 7? Oh dear. Okay. So 14 divided by 2 is not 2, it's 7, isn't it? Of course. So change that one. It should be 7 meters per second squared. Right then, number 2, a car accelerates from rest to a speed of 30 meters per second in 12 seconds. Calculate the acceleration. So again, you write out A equals delta V divided by T. This time we're going to use brackets because remember in maths when we're using BIDMAS, the brackets tell us to do that part first. So we take the final velocity of 30 minus 0 and then we divide that by 12. So you'd always do the bit in brackets that was first. And so then 30 divided by 12 comes out as 2.5 meters per second squared because that's the unit. Third one then, slightly different here because you don't have the at rest. And again, I just want to point out the brackets. So we're doing what's in the brackets first. So the final velocity was 37 minus 22. And when you work that out then, you then divide that by 2 for the time because it was 2 seconds. And you get the final answer of 7.5 meters per second squared. Number 4, a rocket launching in the Ukraine accelerates upwards from rest to a speed of 12 kilometers per second in 8 seconds. Calculate the acceleration. So this one is designed to test you because it's got it in kilometers, and so we don't want that, okay? So what we should have then is we should have the final velocity of 12,000. So all you do is you're adding 3 noughts to change it from kilometers to meters. So 12,000 minus 0 and then divided by the time of 8 seconds, and you should then get an answer of 1,500 meters per second squared. And then the last one, you had to do 2 parts. So that's why they're in bold, because they sort of go together for number 5, because we needed to work out the acceleration of the cyclist, then the acceleration of the car, and then work out which one is bigger. So for the first one, the cyclist, the change in velocity divided by time is 8 divided by 3, which is 2.7 meters per second squared. And then the second part is to work out the acceleration of the car, which is 30 divided by 8 and comes out as 3.75 meters per second squared. And then go back to the question, is this acceleration of the cyclist bigger than that of the car, which accelerates? And the answer is no. It's not the bigger number, so it's not the bigger acceleration. So the answer is that the car accelerates faster than the cyclist. Okay, sorry for the first one where I forgot to put that it was actually 7, so I need to go and correct that after this. Apologies. Okay, so here we then start to think about velocity time graphs. So what I want you to see from the image, first of all, is that if we just work across the 4 and we just call the first one number 1, we can say that the velocity is constant. Okay, so the velocity is constant, it's not changing. It could mean that, for example, you're traveling at 30 meters per second north, and that is constant, it's not changing. Obviously then for the second one, the velocity is increasing, so you're accelerating. And then for the third one, there's 2 different trends. You've got acceleration for that first section, and then at a point it then starts to decelerate. And you could then be asked to work out the maximum velocity from that point, so you could do that. And then in the last graph, you can see that the velocity is decreasing, so we would call that deceleration. And all of the area below the line is the distance, okay? So anything below the line is the distance. And then we can also work out from the gradient of the graph the acceleration. So let's look at that now. Okay, so here's an example of a graph, and I'll show you now how to determine the acceleration. So it's a bit like what we did the other day. So you've got your diagonal line, and you would then draw on your triangle, or turn it into a triangle, and you'd work out your y. So the y for this one is 12, and the x for this one is 3. And then obviously 12 divided by 3 would then give us the answer of 4 meters per second squared. So the technique is the same as what we did the other day. So you're taking that diagonal line, you're drawing on that triangle. I would normally draw it on in dashed lines. And I'd work out my y, which in this one is 12, and my x, which in this one is 3. And then 12 divided by 3, it's always y divided by x, works out as 4 meters per second squared. So that's how you do that one. So what I want you to do now is pause the video in just a moment and calculate the acceleration of the car in the first 20 seconds. So it's that first kind of diagonal line that you need to work out. Okay, and you can do this in your books, and you can write down what is y and what is x, and then do y divided by x. Give me an answer and make sure you've got a unit. Right, sorry, I just lost my connection there. Just want to go back then. So sorry, so as I was just explaining, so you worked out the acceleration of the car in the first 20 seconds. So let's look at that then. So what we would do is we would work out y, which would be 12, and then work out x, which would be 20, and then 12 divided by 20 gives us a final answer of 0.6, and then the unit is meters per second squared. Okay. So you would actually still get marks if you wrote out A equals delta V divided by T, and if you used incorrect values from the graph. As long as you showed that you were working out y and x, even if they were still wrong, you would still then get 1 mark instead of 2. So it's really important to show you're working, to show what equation you're intending to use, which is why I keep trying to show it to you in a very similar format, okay? So you're taking the diagonal line, it originates from the origin, so it's a directly proportional relationship up until 20 seconds, and it worked out at 0.6 meters per second. Okay, so on this next task then, you've got these 4 lines, A, B, C, and D in their different colours, and you need to match the journey to the description below. So one of the lines is constant velocity, one of them is slow acceleration, one of them is deceleration, and one of them is fast acceleration. So can you write in your books A, B, C, D, and then next to them one of those key terms? And then when you've done that, which journey shows the speed changing most rapidly? Which one has the highest acceleration? So whichever one you work out as the fastest acceleration, it'll probably be that one. So pause the video and come back when you've worked that out. Okay, so then for A, you should have constant velocity equals c. So that horizontal line, the velocity is not changing, so it's a constant velocity. The slow acceleration is d, so it's quite a shallow, it's not a steep line. It's going up, but not very high. It's not very steep, so it's got a slow acceleration. And then A, the line is going diagonally down, so that's deceleration. And then the fastest acceleration then is B. Okay, so B has got the fastest acceleration, so it's got that steepest line. And again, I seem to have made another mistake now. Which journey shows the speed changing most rapidly? I don't know why I wrote A, because, oh, actually, no, it is A. Of course, it's got the steepest line, just because, sorry, no, it is right. A has got the steepest line, it just happens to be a down line, so A is actually steeper than B. Sorry, I was just looking at it thinking, why is the answer not B? But it's not, because A is actually steeper, it's just going down. So it's got the most rapid change in speed. Okay, thank you, sorry. Right then, next task, and time to do some drawing here. So this is where you need some graph paper. So you can pause the video and go and get yourself some graph paper, or if not, just use your exercise book. It will still work okay. So a traffic police car is stationary. That means it's got a velocity of 0 meters per second. Okay, so stationary in a motorway lay-by and is passed by a speeding motorist travelling at constant speed of 40 meters per second. So the police car is stationary, but the speeding car is at a constant speed of 40 meters per second. Now you should be thinking at that point that that constant speed is going to be a horizontal line on the graph. At the exact instant the speeding motorist passes the police car starts to pursue. So it's on the chase now. And after 3 minutes of constant acceleration, so the line's going to be going diagonally up for the police car, it catches up with the motorist still travelling at a constant 40 meters per second. At this point, the police car has a velocity of 80 meters per second. So at 3 minutes, the police car has a velocity of 80 meters per second. So we need to draw this as a velocity time graph, okay, for A. And what you need to do is you need to do your x-axis is time, And you don't need to go beyond 3 minutes. So you just write 1, 2, 3 along the bottom, and that's your time. And then your y-axis is velocity, and your highest number is 80. So you could go up in tens, up the side, and then go to a maximum of 80. Remember key information, the police car starts at 0. So you could do a cross there on your graph. And the speeding motorist has a constant speed of 40 meters per second, which means you should see a horizontal line. When something's got a constant speed or a constant velocity, it would be a horizontal line. But the police car, when it starts to pursue the motorist, that will be accelerating. So acceleration is going to be a diagonal line up, and at 3 minutes, it has a velocity of 80 meters per second. Okay. And then once you've drawn your graph, so you can either pause now and get on with the graph and then come back, or just listen to this next bit too. You then need to use your graph to show that at 3 minutes, both vehicles have travelled the same distance. So to work out distance, which is the area under the line, we use shape. So we're working out area basically. And for a rectangle, you would do your base times your height. And for a triangle, you do half times base times height. Okay. So again, at any point now, if you're getting stuck with this, just send me an email because I am available to help. Okay, and then in a moment, I'll show you what this all looks like. So pause the video and then come back when you're ready to see what it might look like. Okay, so here's one I made earlier. So we've got the x-axis, and I've done it in seconds. So the maximum we said was that we needed to go up to 3 minutes, but I think I chose to go up to 4 for some reason, but never mind. So time in seconds, because it just makes the calculations easier. And then velocity meters per second, so I've gone up in tens up to a maximum of 80. And then you can see that you've got that horizontal line for the speeding motorist. So just a constant speed of 40, and then it's labelled as the speeding motorist. So if you've not put a label on your graph to say which line is which, can you do that? And then you've got your traffic police car. So it starts at 0, it's at rest, remember it's in the motorway lay-by, and then it reaches 80 meters per second at 3 minutes, which is 180 seconds. So that was what you needed for A. And then the next question was to show that they have the same distance travelled. So if you start with a speeding motorist, you should start to recognise that you've got a rectangle. And what you do then is you do base times height. So the base is 180 times a height of 40, and you get the answer of 7,200 meters. So you're just working out the area of a shape, and for that one, it was a rectangle. And then you should see as well that your traffic police car is a triangle if you were to draw a dashed line down from the top. And so for this one, you do half times base times height. So 0.5 times 180 times 80 equals 7,200 meters. So it's the same. So they were traveling at different speeds, but they've actually traveled the same distance. And then you could say a question like, well, at what point are their velocities the same? And I would find the point where the lines cross over, and then I'd read down, and then I would get to 90 seconds, and I'd say at 90 seconds, their velocity is the same. So you could also extrapolate that from the graph. Okay, so last thing then is to work out another equation called uniform acceleration. And I'm just making the point that this needs to go on a revision card. And to be honest, your ability to understand this will really depend on how confident you are in terms of maths, that when you've got an equation, when you're doing algebra, you need to get the one that you're trying to work out on its own. And if you change the side, you also change the sign. So if that's not making sense to you, that's something that you could be practicing in maths. So we want to work out something's uniform acceleration. So we have this equation. So V is final velocity. So you have final velocity squared minus the initial velocity squared equals 2 times acceleration times distance. And you will always be given 3 bits of information, and then you'll just have to work out the 4th. Okay, so you'll always be given most of it. So you could be given the V, the U, and the A, and you might have to work out the S. And if that's the case, if you're working out s, then you need to get the 2 and the a over onto the other side. And remember that rule, if you change the side, you change the sign. So if you've got something that's times and you move it over, it becomes divide. If you've got something that's plus and you move it over, it becomes minus. So pause the video, write all of this key information down, because then we need to work on an example together. Okay, so here's our example. A biscuit is dropped 300 meters from rest. So the 300 meters, okay, is our distance. So that's our S. So when you're reading questions, I would, above 300 meters, just put S, or I would just write distance above it so that I know. From rest, that's the initial velocity. So that's U. So I'd put a U above the rest. From the Eiffel Tower bit is actually irrelevant. It's not going to help you with the calculation. Calculate is final velocity. So we want V. So we know what we want. And they've also given in this a question that acceleration, so A, is 9.8. And a slightly different way of saying 9.8 meters per second squared is to write meters per second. Okay? So what we have now is we need to think about how we rearrange the equation. So we need to get v squared on its own, and then eventually when we've worked out v squared, we'll have to square root it. So remember that initially, if you've got it written down from before, it said v squared minus u squared equals 2as. But when you move the u squared over, the minus becomes a plus because you change the side, you change the sign. Okay? And so you simply then would work out 0 squared plus 2 times a, which is 9.8, times 300 meters, and you work all of that out and you get v squared. But in order to change it from v squared to v, you just have to square root it. So this is why you need your scientific calculators. And you come out with the final answer of 76.7 meters per second. So remember, it wants final velocity, not final velocity squared. So this is all about knowing how to rearrange an equation to work out the one that you want on its own. So you move things away from it, and if you change the side, you change the sign. Okay? So now it's time to practice. Okay, so this time, an aircraft lands on the runway at a speed of 40 meters per second, and it brakes to a halt in a distance of 860 meters. Calculate the deceleration. So the first thing to know is what are we trying to work out, and that's A. Because A, acceleration, deceleration, the change in velocity, that's what we want. So we're working out A, okay? And it starts at a speed of 40, so that's its initial velocity, and it brakes to a halt, so its final velocity is 0. So it goes from an initial velocity of 40 to 0. And then it stops in a distance of 860 meters, so that's the S. So when you look in the green box, that equation is that standard equation, and we're trying to work out A. So we need to get A on its own. So we're going to take 2 times S, and we're going to move that over to the other side. Now, if we do times and we move it over, then obviously that changes to divide. Okay, which is why it changes and it becomes divided by 2 times S. Okay, so then we start to put in the numbers. So what is our final velocity? It's 0 because it comes to a halt. What was it at the beginning? It was 40. So you do that bit first, and then you divide that by 2 times 860. And remember, why is it divide? Because they were on the other side and they were being times, but when you moved over, then they become divide, and you get a final answer of 0.93 meters per second. And actually, that should be meters per second squared, technically. Oh, and it's minus, by the way. I'm only just spotting that little minus sign. So it's because it's a deceleration is a minus number. So it's minus 0.93 meters per second squared. Now, this does take a bit of practice. There's not going to be tons of questions on this. So if you're thinking, oh my God, I can't do this, I'm not feeling very good about this, don't think then that you can't do all of physics. Like there, in an exam paper, there would be one question on this. You're not going to get 6 questions all about calculating uniform acceleration. But it's about you being confident with your algebra and understanding that you've got to get the one you're trying to work out on its own. So you move everything away. And if you've got something that's divide and you move it to the other side, it becomes times. And then it's all those other alternatives. So we can practice this when you come back to school, but don't freak out if you're thinking right now, this is a bit tough. So let's do an exam question then to apply this. So we want to extract the information from the question. So the wheelchair starts from rest, it accelerates at a constant rate. So remember, it started off as 0. So the initial velocity was 0. So I'd put next to the question, u equals 0. Then it accelerates at a constant rate till it has a speed of 1.5 meters per second. So I'd be writing next to that v, because that's its final velocity. So we'd have to do 1.5 meters per second squared. Okay. Now you could already then be putting those numbers in onto the left-hand side of the equation, because we could say v squared, which is 1.5 meters per second squared, minus 0 squared equals, and then we'd work out the other bits. So then we've already got the 2. It travels a distance of 2 meters while it's accelerating. So then calculate a. So we know it's 2 times question mark for a times 2 for the distance. And then what we're going to do is, just like the previous example, we need to have the a for acceleration on its own. So we move that 2 times 2 over to the other side, and we do divided by 2 times 2. And I'll just give you a moment to work all that out. So pause the video and come back. Okay, so let's see how you're getting on with this. And so here's that information going in. So that's that final velocity 1.5 squared minus the initial velocity of 0 squared equals 2 times a times 2. So that was what we talked about. And then you then do your 1.5 squared divided by 2 times 2, because you moved it over from the other side. And you get a final acceleration then of 0.56 meters per second squared. And that would get you 3 marks. Okay, so that's that one. Well done if you've got this right and you're feeling confident about it. And if not, we can do some more practice on it when you come back and see how you're getting on then. Okay, so next question then is the same equation. For this one, I just want you to have a go on your own. So pause the video and work out. Remember, you can write the question and you can put what each number means above it so that you know exactly what you're working out. So pause the video and then have a go. Okay, so let's check the answer. Okay, so for this one then, we are working out the initial velocity. So we're working out u, okay, which means that what we're going to have to do is move v squared over to the other side. So let's be working this out then. So a lorry travels 84 meters. So that's our S, okay. I'm just going to write this out. So we know that the lorry travels 84 meters. It's got an acceleration of 2. And obviously then on the right-hand side of the graph, you can do 2 times 2 times 84 meters. So I'm just going to work that out. So for the side of the graph that is 2 times a times s, you should have that side as coming out as 336 for that side of the graph, okay? And then we need to know what v squared is. So it says in the question to reach a final velocity of 19. So what we've got now is we need to have 19 squared minus question mark for u, because we don't know what u is. And we're going to have to do some square rooting as well. Sorry about that, my phone just pinged. And so what we now need to do is move the v squared over. Okay, so you've got everything you need on the right-hand side. So you've got 2 times a times s equals 336. Then we need to get u on its own. So I'm going to move, there's a few different ways that you can do this, but I'm going to move v squared over to the other side. So we would then say that if you move it over, it's still minus 19 squared on the other side. So on your right-hand side, you have 336 minus 361. And that then comes out as minus 25 on your left-hand side. So when you have two minuses, obviously they all cancel each other out. So you have 25 squared. And then when you square root it to get u on its own, then 25, the square root of 25 is 5. So the final answer then is 5 meters per second. And I'll try and find the visual for that as well and put it up in the lesson link so that you can see it in action as well. I realise I've not put it in. Okay, so quick question then. What does the area under a velocity time graph represent? So literally just a moment. And it's this one, it's distance travelled. And then another quick one, which graph shows the velocity of the car, shows how the velocity of the car changes as the car accelerates. So which one, A, B, C, or D, shows acceleration? So very, very quick. And the answer is B. And that is the end of the lesson. Okay, so sorry about some of the things that I forgot to put in. I will post them as additional links that you can look at them. And remember that various parts of this lesson, some are quite simple and other bits were a bit more challenging. But when we've got some of these challenging elements, we can do more practice when you come back, because sometimes it's a bit easier to be there in person to do it rather than me explaining it over a video. And also, then, you know, there are only going to be one or two of these types of questions in the paper, so don't worry too much. Right, I'll see you tomorrow then.